Hi, I'm Hila, and this is my final project in CSCI S89, Data Transfer Anomalies with DNN. Our agenda for today is first meet the HDFS dataset, talk a little bit about data transfer log that stands for 15% of the logs in the dataset. However, those are present in all sessions. Discuss a little bit about class imbalance and also outliers. Then we will see what are the features present in the dataset, which will be categorical and one-hot encoded, and which will be numeric that require scaling. We will then move on to the methodology in modeling the HDFS dataset. Given that the dataset includes nearly 99% of normal logs, even a native model that always votes normal may yield near perfect accuracy, so we will fight this tendency with both stratification and optimization with class weight. Given that we will review 5 different networks, we will talk about the techniques to compare the models, or in our case, using the F1 score. And moving on to the results of the models, we will review the performances of the LSTM models with 25 epochs, as well as the other 4 models that did not perform as well. We will wrap our discussion with some conclusions on this report and suggestions for the next step. So let's start with introducing the HDFS logs, which simply stands for Hadoop Distributed File System. It is a file system that is designed and distributed by Apache, which allows a relatively simple scaling from a single Hadoop cluster to thousands of nodes. Each HDFS environment records the activity logs and then stores it for possible analyses and monitoring. The researches detecting large-scale system problems and a large collection of system log dataset for AI-driven log analytics generated the data used in this project from private cloud environments using standard and typical workloads. They manually labeled data to either normal or anomalous session. There are a total of 11 million log records, which belongs to 600,000 unique sessions. The dataset we work with looks as follows, and there we can see on the first column the node group ID, the node ID in the second column, the log level in the fourth column, and then free text to record the action taken. While each log record is written differently with the free text, this final project focuses on data transfer logs. These logs are nearly 15% of the entire records, or in other words, 1.7 million records to work with. They are present in 100% of the sessions, and most importantly, they're very simple to model. Given the static text of session ID, indication that there is a data receiver and then a mention of the source IP and the port plus the destination IP and port. But there is actually some further patterns when we decide to model the data transfer logs. It turns out that 98% of the sessions include exactly 3 data transfer logs in them, but also the remaining sessions with any count of logs from 1 to 13 demonstrates a much higher percentage of anomalous sessions. So I'll treat those sessions as outliers, drop them from the dataset, and keep a set of 600,000 sessions with 3 data transfer logs each. Now that we have our trainable dataset, let's discuss the feature selection process a little bit. We recall that the log messages are all sharing a similar pattern, so potentially we have 4 features to work with: source IP, source ports, destination IP, and destination ports. But there are also few surprises there. When looking on the destination IP, we see that it's always similar to the source IP, probably because the data transfer happens within the same HDFS node group or node ID. And then when looking on the destination port, we will always have the same value, so it might be a good idea to drop these 2 features. But what about the source IP and port? Well, when it comes to the source port, there are quite a bit much of distinct values, but given that all ports are high and not preserved, it means that closed ports are typically used to perform the same actions. So it might be a good idea to include that feature as numeric. And scaling can be done similarly to an image scaling, so I'll just divide it by the maximal present port. And last, when it comes to the source IP, the dataset demonstrates 203 unique IPs across 1.7 million activity logs. There's some good news actually, because IPs that are close in numbers does not necessarily tell us anything about the closeness of the physical nodes, so it's probably the best to use it as categorical features and one-hot encode those 203 values. So to conclude, we have one feature that is the source port, which is numeric and scaled down to a range of 0 to 1. We also have a second feature of the source IP, which is categorical. And also we know that each session contains exactly 3 logs that we want to bind together. So we have 204 features times 3. That is a total of 612 features for every session. However, how can we be sure that the DNN is even required here? I went on and fitted a logistic regression based on the source port alone, only to discover that it performed probably as good as a random model. Also, when I checked the correlation between the source IP and the label classification, I learned that all 203 IPs appear both in the normal logs and in the anomalous logs. But hey, these are some good news for us because the DNN is required here to understand deeper connections of the source IP and the source port to the classification. And now, before we dive into the 5 models I used to feed the HDFS data, it's probably time to mention the class imbalance that required a special treatment in that final project. First, the data was split to train and test using stratification. That means that both train and test set contains approximately 1.2% of anomalous session. This approach is highly important when working with sparse anomalous labels, so we can secure train and test sets with similar characteristics. But also, if we want our model to optimize the class imbalance and not just simply classify everything as a normal log and get 98.8 accuracy score, we should probably add more weight to the anomalous logs. Therefore, the strategy for this model optimization was to use binary cross entropy with the class weights obtained from the train set. When we will execute our 5 models, we want to be able to compare them in a logical way. Simply accounting for accuracy metric will not do so well with the class imbalance and probably make us just choose the model that tends towards normality. But also precision and recall may not be the best ideas, as precision will push us to choose the model that mostly classifies as normal, and recall would lean towards classifying everything as an anomaly. But the measurement that may work here is actually F1 score, that accounts for both precision and recall and may make us choose indeed the best model that handles this class imbalance. So now that we are ready, it's time to train our 5 models. Perhaps locally this will not work, given that we are working with a quite large dataset, but it's nothing that a quite expensive SageMaker kernel cannot solve within 6 hours. I'll start with a fully connected network to set the baseline for my data. Given that we have 612 inputs, we don't want our hidden layer to include 2 of a radical change, so we will have 3 hidden layers, one with 128 neurons, one with 64, and one with 32. As for the activation function, I'll just use the defaults, so it will be ReLU for the hidden layers and a sigmoid activation for the output classification layer. The downside of this approach is that we get a total of nearly 90,000 trainable parameters. And given that we only have 600,000 trainable examples, it wouldn't be a surprise if that model overfits. So after 50 epochs of training, with a binary cross entropy loss and weights to correspond to class imbalance, the network classified about 63% of the normal logs as such and misclassified 37% of these as anomalous. When it comes to the anomalous logs, the network classifies about 45% of these as normal and 55% of these as anomalous. These are actually not the worst results, and the network did capture the general trend in the validation set, regardless of the possible overfit. But let's also see what happens over the epochs. If we visualize the accuracy, the precision, the recall, and the F1 score, where each plot, the x-axis is the number of iteration, and the y-axis is the metric score, the purple line stands for the train set, and the dotted pink line is the test set. We see that all precision, recall, and F1 metric demonstrates a big difference from the performance of the train set compared to the test set. This is not surprising at all, given that we have so many parameters in our network, and perhaps a bigger data set would do better here. Let's also explore the other networks I've trained. First, I've tried to separate the encoding task from the classification task, hoping to let each network focus on a single task. But unfortunately, with the 4,205 trainable parameters, the network classifies nearly 80% of the normal sessions as anomalous and only 82% of actually anomalous sessions as such. So probably the separate encoding wasn't such a good idea. But also, when we examine our other metrics over the different epochs, the precision, recall, and F1 score all demonstrates a big difference from the train set to the test set. So we're still overfitting with much worse performance. When it comes to RNN, given that we are experimenting with sequences after all, our network architecture did include a quarter of the parameters of the fully connected layer, with two hidden RNN units with 64 and 32 neurons in the hidden layers, then one additional hidden dense layer before we reached the output. This network classifies about 79% of the normal logs as such, and only 43% of anomalous sessions as anomalous. So it looks like it performs worse than a fully connected layer. At least in terms of overfitting, we do slightly better in precision, recall, and F1 score, where the train results and test results are not that different. Considering a bit more sophisticated neuron architecture, we may also consider a GRU. In this design, we will just switch the simple RNN layers to GRU layers, but remove the third dense layer. Such architecture is probably doing the worst because it classifies 55% of the normal logs as anomalous and only 74% of anomalous logs as such. Probably not the best prediction. And when we observe our four metrics compared to the RNN, it doesn't look like we're doing much better in terms of overfitting either. And now it's probably time to announce the winning model. In our case, the best performing model is LSTM architecture in the 25th epoch. The architecture of this network is quite similar to the RNN, only changing the simple RNN layers to be LSTM layers. This has a downside of, again, having too many trainable parameters. However, in our case, it did not interfere with the network from outputting the best F1 score. That network classified 73% of the normal sessions as such and only 47% of the anomalous session as anomalies. These are probably not the best results in the world, however, they did yield the best F1 score, so it is announced as the winner. In terms of metrics, we do see a tendency to overfit in the precision, recall, and F1 score, but this is probably not a surprise given the huge amount of parameters that we trained the network with compared to the number of observations we have. And now, as a closure, perhaps we can conclude some final thoughts. First, the LSTM is the winning model in classifying HDFS logs and demonstrates stronger tendency to classify anomalous sessions as such. Second, despite the stratification, feature selection, and engineering, working with large data sets and paying extra attention to selecting metrics, none of the models performed extremely well. And last, it could be that we could improve our performance with a larger data set, different architecture, and more hyperparameters that could yield better results. And who knows, that may even happen in the next semester.